Welcome to this primer on graphs. Graphs are fundamental objects in discrete mathematics, and it is a good idea to familiarize with them once you venture into mathematics that is beyond high school. Also, it is very useful in Olympiad-style questions. So this lecture is about motivating the notion of a graph, and that will be done via the means of a puzzle. So here is the puzzle. We have a chessboard. Well, it doesn't really look like a chessboard. It has a weird shape, but that's okay. And you have a knight, which one asks to travel from some starting square. It chooses to start at some square, and now it has to travel so that it visits every square in such a way that it visits every square exactly once, except for the starting square where it is required to come back to. And obviously, the knight is required to make only knight moves. So if you do not know how knights move in chess, and knights are also, they look like horses. So if you want to know how a knight moves in chess, you can do a quick Google. Basically, it's a kind of an L shape in which they move. So if the knight is here, it can go 2 steps to the right and 1 step up, or 1 step up, 2 steps to the right, 2 steps to the right, 1 step down, etc. Okay, so the question is, the knight is required to visit every square exactly once, except for the starting square, where it is required to return to. So maybe the knight decides he wants to start here, and then he has to visit everything. Sorry, not that. Here, sorry. Go here, and then maybe, I don't know, here, then here. So this is how he is allowed to move, and he cannot visit any square more than once and return to the starting square. So he's in some sense visiting the starting square twice. All right, so I hope the problem is clear. And what is the problem? So the problem is it even possible to do so? Can the knight find such a path? And if yes, then find such a path. All right, so I do not want you to attempt this problem or anything. I just want you to play along so that we can see why the notion of a graph just pops out of this puzzle. All right. So we have labeled the unit, little squares that we had, 1, 2, up to 12. And abstractly, we will denote them by dots. So every little square is now in this abstract picture that we'll draw is represented by a dot. Okay, and now here is what we will record in this abstract data is the following. Suppose the knight is somewhere, let's say 5. Then we want to record where all it can go. So if it is at 5, then it can go to 7, it can go to 11, it cannot go anywhere else if it is at 5. Similarly, if the knight were at 2, then it can go to 3, it can go to 8, it can go to 10. So all this data we want to record. So let's start with 1. Sorry about that. So if we start with 1, from 1 the knight can go to 7 and to 9 and to 6. These are the 3 squares that it can visit. So from 1 it can go to 7. So I will join them via an edge. It can go to 9. So these are joined. And it can go to 6. So these are joined. Okay. Let's now do the same thing with some other thing. Let's try 6. So it can go to 12, it can go to 8, it can go to 1. So from 6 it can go to 12, 8, and 1. So 1 was already joined. So we do not have to rejoin it. Okay, so similarly, we will develop this entire crisscross. It will be a complicated thing, which I have already drawn. So it will look like this, the whole. If you do it for every square, you will get this picture. And now here is a sequence. So what is this sequence? Basically, what does this picture tell us? Suppose I want to find out where I can go when let's say I start at 7 and I want to journey around. This data helps me schedule my journey. So suppose I want to start at 7, then I can go to 12, and then I can go to 4, and then I can go to 10, and then I can go to 2, then I can go to 8, 6, 1, right? So it is giving me a catalog of which city to visit next, right? And the constraint that we are given is that once you visit a dot, you're not allowed to visit that dot again. And you have to return to your starting dot. So now we can forget about this. This is just some abstract data, and we just have to, play that game where can you find a closed loop here which visits every city but returns to the starting city. And it's not easy to do that. It takes some guesswork, something, or you can write a program to find it. And this is, this sequence that I found is just a matter of computation. This was not found out using some deep mathematics. So let's see what does this do. So if you start with a 9, then you can go to 1, you can go to 6, 8, 2, then 10, 4, 12, 7, 5, 11, then 3 and a 9. 3 and 9. So we started at 9, we ended at 9, and we visited every other thing exactly once. And this is a very convenient way to find such a path. So this is a solution to our problem, right? This particular path is a solution to that night problem. All right, so now we can formally define the structure. This is an instance of what is known as a graph. So formal definition follows. A graph is a pair. So it has two things, V and E, where V is a set, a non-empty set, and E is a collection of subsets of V, each having size 2. So it's not clear what this is saying, but this is the formal precise definition. In symbols, one can say E is a subset of those subsets of V which have size 2. Right? Graph is a pair like that. And 1 second. And this is called the vertex set. This is called the edge set. An element of the vertex set is called a vertex of the graph or a node. So there are these terminologies. We have vertex, we have node. Is there something else? There are other terminologies I'm not able to remember. Yeah, but for now, these two things come to mind. So these two things mean the same thing. And everything in E is called an edge. E can possibly be the empty set. That's okay. I mean, E could be the empty set, but V is not allowed to be empty. Okay? So that's the definition. And let's see examples to foster our understanding. So suppose we have drawn this picture. This is what we want to really think of as a graph as. The picture is most important. So you have some nodes and then some lines which inform us as to which node is connected to which node. But a mathematical object has to be expressed in a formal language. One cannot just draw a picture and expect people to understand what is being said. Although when you're talking to someone, explaining something, even in a talk or in a research paper, it is fine to draw pictures, but when defining things for the first time, a picture is not sufficient. We have to formalize what exactly we mean. So when we draw a picture like this, the graph that we are really talking about is a pair V comma E, where V is the set of all the nodes, and E is 2-element subsets. Which ones? This 2-element subset and that one. 1, 2 and 1, 3. Okay, so this finite data, or whatever you want to call it, this is really the object that this is trying to capture. Okay. Another example, here we have 4 nodes which are labeled A, B, C and D. So what is this trying to capture? This is trying to capture the graph G, which is again a pair of 2 things, V and E. V is the 4 nodes, and what are the edges? So the edges are, you have AC, you have BT, you have CD, and that's it. 3 edges. Okay. So that's that. There are many things that we will learn about graphs in subsequent lectures, but I think for now this should be enough. Here, if you are going to write down the full description by hand, it will take a lot of time. There are a lot of edges. Okay. So I hope it was clear as to why graphs are important. They capture relationships between a finite data. You can think of the edges as capturing relationships. And one thing I want to emphasize is that a graph, when we draw a graph, it is not meant to be anything to do with the plane in which we draw it, or the geometry of the edges. We may draw a squiggly thing and that is as good as the straight thing. And crossing here has nothing to do with this data. This data has no crossing or anything. So how you represent a graph is irrelevant, whether you draw it this way or the same thing could have been drawn in this way, the same graph, the one that we see. So how you draw the graph is irrelevant, because the formal object is this, which does not have any bearing on how you draw the graph. Okay, it is a very interesting question. Drawing graphs on surfaces is a very interesting question in its own right. But as a matter of definition, it has nothing to do with it. Alright, so I think this is enough. As usual, like, comment, share, subscribe, and I will see you next time.